if you are running a business,
GIAN, if you consider this as a Hindi word, it means knowledge. It is a word deeply rooted in wisdom and enlightenment, signifies the path to growth and transformation. As the great philosopher Socrates once said, wisdom begins in wonder, knowledge empowers, wisdom elevates, and learning paves the way for a bright future. At this moment, I would like to request Dr. Saurabh Kumar Katiyar sir, the course coordinator of the GIAN course, to deliver the welcome address and shed light on the objectives of this program.
अभी देखना सही है, सही है ना? है? उससे शायद कुछ दिक्कत है सर. So a very good morning to everyone. On behalf of the Department of Mathematics and Computing, Dr. B.R. Ambedkar, NIT Jalandhar, it gives me immense pleasure and honor to extend a warm welcome to all the distinguished dignitaries, esteemed guests and enthusiastic participants present here for the inaugural ceremony of the Global Initiative on Academic Network known as GIAN. Course on Understanding Fractal Geometry through Visual Constructions, organized during March 25th to 29, 2025. As we know that GIAN is one of the schemes funded by the Ministry of Education, and I am Dr. Saurabh Kumar Katiyar, and as a representative of the department, I take great pride in welcoming our esteemed chief guest and guest of honor, Professor Andrei V. Tetenov from Sobolev Institute of Mathematics, Russia. We welcome you, sir. We are deeply grateful to you, sir, for graciously accepted our invitation and gracing this event instead of your very busy schedule. And 15-20 days he told me that he was suffering from some illness and he is not able to come, and he requested that can we extend our GIAN course 15-20 days back. Then I requested him that participants are coming all over the India and they have booked the ticket, and it will be very difficult if they will reschedule their time and date. And then sir told that okay, I will take some medicines and I will rest for some days and I will try to come. So thank you so much, sir. Now it is great privilege to welcome Dr. Raghav Raman Sinha ji, Head Department of Mathematics and Computing, NIT Jalandhar. Sir, we welcome you, sir. We are delighted to extend a hearty welcome to the local course coordinator, Dr. Vimal Kumar ji, Department of Chemistry, NIT Jalandhar. Sir, we welcome you, sir. And it is my pleasure to welcome Dr. Geeta Pratam Madam ji, Department of Mathematics and Computing, NIT Jalandhar. We welcome you, ma'am. It is my pleasure to welcome all the deans and head of the departments of various departments of NIT Jalandhar to the inaugural ceremony of this GIAN course. I extend my wholehearted welcome to all the learned colleagues, enthusiastic participants, press and media, dear professors, scholars and students. I extend my wholehearted welcome to all our 48 participants, those who come from 16 different states of India, covering from Kerala, Tamil Nadu, Andhra Pradesh, Uttar Pradesh, Punjab and including Kashmir also. And we welcome you all on behalf of the Department of Mathematics and Computing and from GIAN side also. Now I want to say few things about understanding fractal geometry through visual constructions. So there are two approaches to the study of objects of the surrounding world. One is based on representation of these objects as consisting of homogeneous parts of simple form. The other suppose that the objects have a fine structure in all scales, in general repeating similar patterns on different levels. So like in daily homemade kitchens we use broccoli. So if you see the broccoli and you take a smaller version of broccoli, then it is having the similar patterns. So first approach gave classical methods of geometry and analysis with differentiable functions and simple geometric forms. The other was abandoned for a long time. Like daily we see the clouds, and if we see the boundary of the clouds, and boundary of the clouds are the continuous curves, but they are nowhere differentiable functions. So in mathematics there are some nowhere differentiable functions like Weierstrass function and Tagazi function. So people were not taking interest in those directions in 19th and 20th century. So it revealed itself in the end of 19th century and beginning of 20th century by many disturbing mathematical phenomena which did not agree with the classical smooth approach, nowhere differentiable functions, as I said, curves having no tangents at any of its points or filling a domain in space, and so on. So in 1975, a great mathematician Mandelbrot coined the term fractal and brought these objects together for the first time and turned them into essential tools for the long-stalled effort to extend the scope of science to explaining non-smooth rough objects in the real world. And now I want to say a few words about the course, this GIAN course. So the course is intended to lead the participants through the main concepts of the theory of self-similar sets, such as different types of self-similarity, fractal dimension, to demonstrate main structural properties of these sets. The teaching will be based on personal investigation of numerous examples and counter-examples and making computer experiments by every participant. So yesterday Tetenov sir was telling that I want to see your classroom as well as computer lab also, because our tutorials will be very advantageous for the students. So this will be realized during the lectures and especially on computer lab works, during which the participant will taught to construct models of self-similar fractals with prescribed properties using fractal construction program packages like IFS stylings, allowing to build high resolution 2D and 3D models of fractal sets. Each of the participants will learn to find the equations of the fractal objects needed and to write a program code defining these objects. We will consider the main tools of fractal theory such as address map, index space, open set condition, and WSP. Different finiteness properties, some graph theory approaches, and special classes of self-similar objects such as Cantor sets, Jordan arcs, self-similar dendrites, fractal squares, and self-similar tiles and multi-tiles. So we are having here the eminent speaker, Professor Tetenov sir, who has served more than 2 decades in this field, means in fractal geometry especially more than 2 decades, and in research more than 4 decades. And I was very fortunate to meet him in a Rajagiri School of Engineering in Kerala, and Professor Samuel Madam is also there. She is from IIIT Lucknow. So we both went to attend that conference and we were fortunate to meet him. From his experience, we are going to have the course being taught in 14 lectures hours and 6 tutorial hours. Also the case studies and assignments will be shared to simulate research motivation among the participants. I am glad to share that our Understanding Fractal Geometry through Visual Constructions 2025 has a speaker from Russia and 48 participants from several IITs, NITs, central universities, state universities, various high NIRF ranking institutes and colleges from India. The registrations include faculty members, research scholars, students from 16 states of India. I wish all the participants enjoy the sessions during these 5 days and have fruitful discussions with the established speakers. I encourage all participants to actively engage in discussions, ask questions, and immerse themselves in the learning experience that this course offers. May this event serve as a catalyst for further exploration and collaborations in the field of fractal geometry and beyond. Thank you very much.
Thank you so much, sir. Now I would like to invite Dr. Vimal Kumar, Local Course Coordinator and Associate Professor in Department of Chemistry, to briefly summarize the GIAN course and its importance.
A very good morning to all of you. Am I audible? Okay. Yes. Yeah. A very good morning to all of you. Today's chief guest, Professor Vinod Kumar Kanodia, Honorable Director, NIT Jalandhar. He could not be present due to some occupancy. Guest of honor, Professor Andrei V. Tetenov, Head of the Department, Dr. R.R. Sena, Madam Dr. Geeta Pratap, Course Coordinator, Dr. Sourav Kumar Katyar, dear faculty members, students, and dear participants. On the behalf of GIAN program and NIT Jalandhar, I welcome you all to this GIAN course organized by Department of Mathematics and Computing. The GIAN program, that is Global Initiative of Academic Network, is a great initiative by the Ministry of Education, Government of India, to enhance the academic structure of India and building the connection among global experts, our students and educators. Through this GIAN program at NIT Jalandhar, we are trying to engage the brightest minds from all over the world with our students and faculty. The program enables the international experts to share their knowledge, collaborate in research, and teach advanced courses that help our students to gain valuable insights. So, these programs provide our students the opportunity to interact with the global scholars and learning from their experience to enhance their academic and professional journeys. Moreover, through these programs, we look forward to the future collaboration and innovation at the international level at NIT Jalandhar. So we appreciate the role of Hyderabad at this stage, because IIT Hyderabad is doing a wonderful work. So it's valuable sport it is there to conduct these type of GIAN courses. So in the current session, we have sanctioned total 11 courses with a budget of worth rupees 67 lakhs throughout the year, and out of these 5 courses have already been completed, and during these courses the experts from various countries like USA, Japan, Korea, Italy have become the part of this knowledge sharing program till now. Apart from this course, 5 more courses will be conducted in the coming months for this session. So we are grateful to our worthy director sir for his constant support and motivation to organize such type of courses. So here we are also thankful to our experts who are sparing their valuable time to share their knowledge. Our course coordinator Dr. Sourav Kumar Katyar, after that the faculty members for their motivation and participation, and all the participants for the successful execution of these kinds of courses. So previously many, you can say, other courses have been conducted, and the participants and faculty members, they have appreciably put their valuable inputs for running or organizing these type of courses. So during entire these programs, I hope comfortable stay for all the participants at the NIT campus. I also welcome the suggestions of participants to make these type of program more successful in the future. So with all these words, I welcome you once again. So thank you for your participation. Thank you for attending these kinds of courses. Thank you.
Thank you, sir, for your motivating words. Now I would like to invite Dr. Raghav Savam Sinha, head of the department, to address the gathering and share a few words about the department.
very good morning to all of you. Today's guest of honor, Professor Andrei V. Tetenov, local course coordinator Dr. Vimal Kumar, course coordinator Saurabh Kumar Katiyar, and my dear faculty members, research scholars, students, and participants. On behalf of the Department of Mathematics and Computing, and my own behalf, of course, I welcome you all to the highly enriching GIAN course on understanding fractal geometry through visual construction, organized during this period of March 25 to 29, 2025. The initiative led by Dr. Saurabh Katiyar marks a significant step towards the exploring and fascinating the world of fractals, a topic that lies at the intersection of mathematics, art, and nature. Mathematics has always been a powerful language to describe the patterns and structure we observe in the world around us. Among its many branches, fractal geometry stands out as an extraordinary field that reveals the hidden order in seemingly complex and chaotic forms. Understanding these structures not only enhances our knowledge but also opens up new avenue for research and innovation. This GIAN course is unique in its approach, focusing on visual constructions to unravel the complexity of fractal geometry. I take this opportunity to commend the dedication and hard work of our faculty member Dr. Saurabh Kumar Katiyar, who has brought this course to fruition. Organizing such an event requires vision, efforts, and a strong commitment to academic excellence. I also extend my gratitude to the distinguished experts and speakers who will be sharing their valuable insights, making this course an intellectually enriching experience for all participants. I hope that the participants will learn a lot in cutting-edge area of fractal geometry with real-world application of interacting with the knowledgeable galaxy of experts during this course. As far as department concerned, the Department of Mathematics and Computing, NIT Jalandhar, is one of the 18 departments of the institute. The department offers BTech and MTech program in mathematics and computing and MSc and PhD program in mathematics. The department also teaches mathematics to BTech, MTech and PhD students belonging to various engineering streams. The department has 17 faculty members who are actively involved in research and regular teaching activities. The faculty members of the department are specialized in the frontier areas of mathematics such as fractal geometry, algebra, matrix analysis, numerical analysis, partial differential equation, mechanics, statistics, optimization, soft computing, etc. The department till date has produced 12 PhD in different branches of mathematics, and presently 37 research scholars are pursuing their PhD. Several research projects of the departments are financially supported by some of the leading funding agencies such as DST, ANIRF and NBHM. The department keeps in pace with the advances in technology by providing the students state-of-the-art computer facilities. The students get opportunity to attending seminar and invited lectures delivered by the eminent mathematicians and academicians. They get the opportunity for campus placement in various national and multinational companies. I am deeply grateful to our esteemed director, Professor Vinod Markanogia, for his unwavering support and motivation in making this event possible. Although he could not attend this inaugural session due to unavailable circumstances, his encouragement has been instrumental throughout. I also like to extend my heartfelt thanks to all the dignitaries, faculty members, staff, and students of the Department of Mathematics and Computing, NIT, for their presence and participation in this event. Last but not least, I express my sincere gratitude to all the participants of this GIAN course for their active involvement. I wish the GIAN course a great success. Thank you very much.
Thank you so much, sir, for sharing insight about the department. With so many attributes to GIAN, it is my great honor and privilege to welcome our distinguished guest and guest of honor and chief guest, Professor Andrei V. Tetenov, to this GIAN course.
So, hello. It's very nice to see all the participants and all the guests. And it is a great honor for me to be invited to GIAN course at NIT Jalandhar. And so I visited this wonderful place, I suppose in 2011 or 2010, most probably in 2011, and I was traveling to Hamirpur, and on the way from Hamirpur to Amritsar, we had a short stop at this place. So it was absolutely different thing. There was absolutely deserted place and only the buildings were, and now I came here and everything is flourishing, and I wish that NIT Jalandhar will flourish further and further, will flourish with science, with clever minds, and with all its students. So thank you very much for inviting me, and I'm happy to present you my lectures.
Thank you so much, sir. Professor Tetenov is an internationally acclaimed mathematician with an illustrious career spanning over 4 decades. Currently, he serves as leading researcher at Sobolev Institute of Mathematics, Russia, and a professor at Novosibirsk State University. His groundbreaking contributions to geometric group theory, hyperbolic geometry, Kleinian groups, fractal geometry, and dynamical systems have significantly shaped these fields. With a Doctor of Science and PhD in mathematics, his research has been widely recognized through numerous grants, invited lectures, and collaborations across the globe, including prestigious institutions in Germany, UK, India, Vietnam, and the United States. Today we are fortunate to have him share his deep insights, enriching our understanding of complex mathematical structures. Let us extend a warm welcome to Professor Andrei V. Tetenov. Now let us bridge the gap with communication, come create another aura with education. There is an end to everything, but we believe that there is never an end, but always a beginning. Thus to conclude for today. Now I would like to invite all the dignitaries to hand over the token of appreciation and a gift to the chief guest. So, please come.
Shelly? Sir. HOD sir. Vimal.
as well as practical challenges encountered and solutions adopted in the field of fractal geometry. We are very impressed and touched by the ability of the participants, and they deserve a round of applause. Thank you, one and all. Thank you once again. Thank you very much.
Thank you, ma'am. I extend my heartfelt thanks to everyone for making this event possible. Thank you all for joining. Now we will have the tea break for half an hour. Then we will move towards the first technical session. Thank you, everyone. snacks arrangement are outside. Just outside.
अभी हम सबके साथ खिंचवा लेते हैं, तो बहुत चाय वाय तो चलती रही है, एक एक
what is the, I need to check the time, and so I need to finish at which time?
At least 1 hour.
At least 12:30. 12:45. Okay. So let us begin. I need to accustom to all this thing. So I will talk about, of course, fractal geometry is very vast. Yes. And it combines very complicated mathematics. At the same, it combines a lot of pleasure in experimenting with fractals. So anyone can find something for his heart in fractal geometry. But main notion in fractal geometry, of course, is the self-similar sets. And I will tell you something about self-similar sets, what you possibly know very well. But we need to agree upon well-established notions. Therefore, I will begin with very simple things, and possibly some questions may turn out to be a little complex, so please give me a sign and I can elaborate them or maybe run through them to the next position. So now there is some self-similar set, as you see. Oh, does it work? Oh, there must be some kind of a, do you remember how can how can I use the buttons here? Let me, no? Oh, I need to use this one. Okay. Thank you.
Yesterday it was working, right? Yesterday it was working.
Yesterday it was working, but each day is different. It was working very well because I was moving this picture as I like. Yes. Oh, yes. Yes, I understand. Yes, I need to use my laptop for changing the positions. Oh, you see. Yes. Okay, let us do everything as it is. Yes. We'll solve this problem afterwards.
Yes.
No, okay. So I will use classical manner, so I will tell you about self-similar sets. So when you talk about fractals, they do not have this smooth structure, and something doesn't allow them to scatter completely. So, and they don't scatter and have the very well established order because of very complicated relations between its smallest parts. So, 1 second. This is my best plan. And this is, okay, the last plan. So suppose we have some, let X be a complete metric space. So I mean a metric space in which each fundamental sequence has its limit. Yes. And we say, so metric space was supplied with the matrix D, XD. We say that F from X to X is a contraction. If there is such Q less than 1, that such that for any xy in X, the distance between f of X and f of Y doesn't exceed Q divided by distance, Q multiplied by the distance between X and Y. Yes. So the minimal number Q for which such a inequality holds for any X and Y in X, non-equal of course, yes, is called the Lipschitz constant. Lipschitz constant is a minimal Q such that this inequality holds for any. So we write it Q is Lipschitz of F. So if this Q is less, if Q is less than 1 and more than 0, yes, then F is a contraction map of the complete metric space to itself. Now suppose we have a is there any duster? Do you see? Can you show me? Ah, yes. Let S be S1 Sm be a system of contractions maps of complete metric space X. So I give the definition of attractor of a system S. Definition. A compact set K a non-empty compact set K for which the equality holds, for which holds the equality such that K is S1 of K union Sm of K, is called the attractor of the system S. Is called the attractor of the system S. Yes. So now you hear it, you see it, and can I magnify? So do you see these small letters? Is it possible for you to recognize? So here I wrote cat code T. It's just the name of the program. Yes, and just the name of the block. This is the name of the program. It is a program called 1. Yes. So I showed that the results of this program should be visible. Dimension is 2. And here I defined 3 maps. This is a contraction, or this is a similarity with contraction ratio 0.6. Yes. This is a similarity with a, which is a composition of 0.6 contraction and shift by the vector 1, 0. Yes. So this is a translation by 1, 0, and this is a composition of contraction 0.6 and translation to 0.5, 0.7. Yes. So this is translation by by 1, and this is translation by 0.6, 0.7. Okay. And then I write that K is equal to S1 union S2 union S3 applied to K. So I have this operator applied to K, and so I can make some changes in this program. So I obtained a self-similar set this way. I can make some changes here and you will see the results. For example, if I make 0.4, you see? If I change one contraction ratio to 0.4, then I got this set. Yes. If I change sum of translation vectors, for example, I make 1.5 and apply, I get this set. Yes. Oh, this is too weird. So let it will be 0. 0. Yes. Yes. And if I wish to see it in larger detail, I can make a magnification. And even larger magnification, and even larger, so I can visualize the structure of this self-similar set in very neat detail. Yes. So now I have shown you this operator S1 of K union S2 of K union S3 of K, and the result of applying this equation is the attractor called K. So if you have a system, then if you have a system S1, S2, Sm of contractions, and mostly it will be similarities, so it will be just multiplication by some number and rotation. Yes, if it is in a plane, then their contraction ratios or Lipschitz constant will be denoted by Q1, Qm. Yes, so it is always very useful to take the maximal of Q's and Q minimal of these Q's, so we will consider these numbers in our considerations. But the first question is, under which condition the attractor exists? We need to prove the existence of this attractor. What should be this contraction maps so that the attractor exists and is unique? So we can ask this question and try to solve it, but to solve these questions we need some additional constructions. So if we have a complete metric space X, then we can consider the space of all compact subsets of X. So we denote by C of X, it will be the space of all compact subsets, non-empty compact subsets of X. Since X is a metric space, then we can define a metric, the distance between these compact sets. And we'll supply it C of X by Hausdorff matrix. Or Hausdorff distance, it will be denoted by dH. So, how to define Hausdorff distance? Tell me please, who knows Hausdorff distance and who knows how it is defined? Can you show me? Wave my hands. Need I explain it in detail, or I can shift it and run further as fast as I can? So not everyone. So I need to elaborate it. Okay, this is very good. To explain what is a Hausdorff distance, I need to write. So if we have two, we consider only compact sets. The Hausdorff distance between A and B is equal to maximum of two values, d of x b, how to say, maximum, sorry, I tried to write shorter, but it is not good. It will be maximum of x in A, d of x to b, and maximum of y in b, d of ya. So I can define it in this way. Do you understand what I mean? So we have a set A and a set B. This means that we take the most distant point in A from B, and it will be D. This distance will be distance between X and B. Yes? And take most distant point in B from the set A. And this will be the distance between Y and A. Yes? And we take the greatest of these two values, and this will be called the Hausdorff distance between two sets. But better to treat this distance in terms of neighborhoods. In terms of neighborhoods, it's much better. We divide for rho more than 0, we define V rho of A. It will be a rho neighborhood of A. It means union of all balls of radius rho with the centers of points in A. So if we have a set A, then rho neighborhood of A will be union of all balls with centers in A of radius rho. Sometimes it is called a rho parallel body of A. Sometimes. Then, in these terms, the Hausdorff distance between A and B is a minimum of all possible rho, such that V rho of A contains B, and V rho at B contains A. What does it mean? So I have, there is only one color. So I have the set A and the set B. So I find the radius of neighborhood of B which swallows A. This will be V rho of B. And find the maximal radius of neighborhood of A which covers, or minimal of course, which covers B. And we compare these two values and take the maximal of that. So it will be Hausdorff distance between A and B. Oh, please, one question. One question to the auditorium will be the following. I lost my duster. It's in, yes. It's near the pen. Okay. I have interval 0, 1 and have the interval 1/2, 3. What will be, so this will be A, and this will be B. What is the Hausdorff distance between these two intervals? How do you think? 2. Yes, okay. And if I take a circle, one second. A circle and a disk inside it with the same center. This will be, for example, it will be 1, and this will be 3. What is the Hausdorff distance between these two sets? What? Now. Oh. 3. Because the most distant point from this circle is the center. Yes. So there are some properties of Hausdorff distance which we need to consider. So we have the following lemma. Suppose we have two families of set. Suppose we have the sets A1, AN, and we have family of sets B1, BN. Then Hausdorff distance between A1 union AN and B1 union Bn is less or equal than maximum of Hausdorff for k from 1 to n of Hausdorff distance between AK and BK. So if you have two families of sets, for example, A1, A2, A3, and we have B1, B2, B2, B3, yeah, right? So the distance between this union and this union is less or equal to the distance between, to maximal distance between these pairs. Yes? Do you agree or you disagree with that? If you disagree, then I will prove. The distance between, consider the row neighborhood of A1 union AN. For any row, this is, sorry. A difference. So, if rho is greater or equal to the right part, then V rho of AK contains BK, and V rho of BK contains AK, right? If rho is greater or equal than this distance Yes. But this implies that V rho of union of AK contains union of BK, and V rho of union of BK contains union of AK. Right? Therefore, the Hausdorff distance between these two unions is less or equal to rho. So it gives us that this Hausdorff distance does not exceed this one. And second assertion in this lemma will be the following. If Lipschitz coefficient of the map F equals to Q, then Hausdorff distance between F of A and F of B is lesser or equal than Q multiplied by Hausdorff distance between A and B. Right? It's obvious. You see, since the distance between f of x and f of y less than q multiplied by distance between x and y, then f of rho neighborhood of A is contained in rho q neighborhood of f of A. Right? This implies that. And then so if this distance is rho, then Hausdorff distance between f of A and f of B will be less or equal than q rho due to these two inequalities. So we have two properties. First, the distance between two unions is less than maximal distance between the respective members, and Hausdorff distance between f of A and f of B is less or equal than q multiplied the distance between A and B. Okay, so keep in mind this lemma and consider the operator. So let S1 Sm be a system of contractions. Contraction maps. We can define the Hutchinson operator of this system. Let T of A denote S1 of A union S2 of A union Sm of A. So this operator sends a compact set to the union of its images under continuous contractive maps. Therefore, this union will be also compact, because the image of a compact set is again a compact set, and finite union of compact set is again a compact set too, right? So T then T is a map from the space of compact subset of X to the space of compact subset of X, right? Because if we have some A in this set, then we'll have T of A, which also belongs to this set, to this space. Consider what happens with the distance. So we have this S1, Sm, and we have contraction ratios Q1, Qm. And all these Q1, Qm are less than Q maximal. Less or equal than Q maximal, right? Then, so we take two sets, A and B, and consider the sets T of A and T of B. T of B. For example, consider three contractions which send this triangle to its parts. This S1, so it will be A, this will be S1 of A, this will be S2 of A, and this will be S3 of A. Yes. And suppose we have some set B, for example this one, yes? So S1 will send B to this place, it says S2 to this place, and S3 will send B to this place. So we need to evaluate the distance between these three triangles and these three, the union of these three circles. Hausdorff distance between T of A and T of B is equal the Hausdorff distance between union of Sk of A from K from 1 to M and the union of Sk of B from 1 to M. Right? If we look at this lemma, then we'll see that the distance between two unions is less than the maximum of distances between their respective members. Therefore, we'll have, it will be less or equal than Hausdorff distance then maximum of Hausdorff distance between AK Sk of A and Sk of B. Sk of A and Sk of B. But Sk is a contraction with the coefficient Lipschitz coefficient Qk, so it will be less than maximum of Qk multiplied by Hausdorff distance between A and B. And therefore it will be less or equal than Q maximal are multiplied by Hausdorff distance between A and B. What we see? We see that the distance between two images of A and B under the operator T is less than Q maximal multiplied by distance between A and B. Right? Therefore, T is a contraction map. So it follows that T is a contraction map on the space C of X. On C of X. Yes, because the images of A and B under the operator T have smaller distance. With Lipschitz coefficient, with Lipschitz coefficients of T less or equal than Q maximal. Now consider the space of all compact subset of X supplied with Hausdorff matrix. There is a very interesting question. Is this space complete? So, it is very pleasant to explain the completeness of the space of compact subsets of a complete metric space, but it needs time. So if somebody wants to have this explanation, I will do it for these persons, and I will, but now I just write, since the space C of X is a complete metric space, the map T has what it has? Has the unique point K in C of X, right? So there is a very vast range of people sitting here. Some are specialists in fixed point theory. Yes, and this is trivial for them, and maybe some do not remember Banach fixed point theory. Do you remember Banach fixed point theorem? Yes. So, if we have a complete metric space, yes, and if we have a contraction mapping of this, then it has unique fixed point. And this point will be a compact in C of X. And this compact will be unique. And this compact will be the attractor of the system S. So it means that K satisfies the equation K is equal to S1 of K union Sm of K, right? There is no other attractor. So each system of contraction maps defines unique compact which is the attractor of this system. Okay, so we have the attractor, and we need to know the structure of K. The problem, what is the structure of the attractor? The first approximation to the structure will be shown on the following picture. I need to slightly change it. For example, I will take this 0.5, this will be 0.5, 5, this will be 0.5, 5, 1, 0, and this will be, okay. So let it will be 0.3, okay. You see. So here is a typical self-similar set, very typical as equilateral triangle is a typical triangle. Yes. So it is generated by 3 contraction maps, S1, S2, and 3. Yes. Therefore, these images of K under these contraction maps will be called copies of K, and we will denote them the following way. K is equal to S1 of K, or we will write simply K1, union S2 of K, we will write simply K2, and this will be K3, S3 of K. This will be copies of the first order. But this song never ends, because each of these copies consists of, again, the same number of copies of next rank. So it will be union of K11, union K12. Do you understand what I mean? K13. So if it is K1, this is K11, this is K12, K13, K21, K22, K23, K31, K32, K33. Right? K33. And on nth step, we'll have the following things. First, we have, if we have M maps, then K is equal to union of K1, Km, and on nth step, it will be K1, 1, 1, 1, n times union K, and there will be K1, 1, 1, 2, etc. And finally, it will be Km, M, 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 n times, right? So this will be the copies of nth order. This is what I said, these smallest particles of a self-similar set have very strong relation between that which is repeating on all scales. And therefore, study of self-similar set always is connected with these copies of different order. So what is relation between copies and maps which generate these copies? So if you have S1, Sm, M contraction maps, then we have the copies K1, Km, as I said. And then we can consider composition as I1, composition as I2, as IN. Yes? So if we have a sequence of indices from 1 to m, then we'll get a word. It will be word I1, I2, IN. Yes? And this word defines a copy. K, I1, I2, IN. For example, suppose I need to find K1, 2, 3, 1. Can you detect it on this picture? K1, 2, 3, 1. So first, K1 is this, yes? K1, 2 is this. K1, 2, 3 is this one. And 1, 2, 3, 1 is this one. So each copy has its own unique address, yes? And by this address we can identify any small region of this set. So if you have two indices, I1, I2, IN, and J1, J2, JN1, JN2, yes, we can compare them. For example, if you have K1, it contains K1, 2, it contains K1, 2, 3, it contains 1, 2, 3, 1, it contains 1, 2, 3, 1, 1, etc. Yes? So there is a relation between these sequences. I will call it multi-indices. Sometimes they are called tuples. Sometimes they are called words. In different textbooks, you have different names for the same things. So we say that one multi-index is how to say, shorter, is a shorter part, is a prefix of the second if n2 is greater than n2 is greater than n1 and I1 in1 is equal to j1 jn1. Yes? If this part is just an initial part in this word, then this word is a prefix for this one. We have a prefix relation. But how this prefix relation is reflected in the structure of copies? If I1, IN is a prefix for J1, Jn2, then Ki1, In, N1 contains K, J1, Jn2, right? Because the longer is address, the smaller is the copy. Yes? And if we have two multi-indices, for example, suppose we have a multi-index I1, In1, and J will be J1, Jn2, yes? We will write I wedge J, the longest longest common prefix of these two words. You see? So, what does it mean? It means, suppose you have 1, 2, 3, 1, 2, 3, and you have 1, 2, 3, 2, 1, 1. Yes? So the longest common prefix will be this one, right? If you have two multi-indices, then we'll have their common part, if it exists. Yes. It will mean that K 1, 2, 3 contains K 3, yes? And K 1, 2, 3 contains K 1, 2, 3, 2, 1, 1, right? So if you have two copies, yes, and take their addresses, then we'll then this notation denotes the minimal copy containing these two ones, right? These two ones. So if we have two copies here, then minimal copy will this. If you have two copies there, the minimal copy will that. If you have two copies there, the minimal copy will be the whole K. So this is the first thing which I could tell you about the relation between copies. Tell me please how much time I have spent and how much time is... What? How many minutes left? 2? 15. Okay. Okay. I need some kind of special watch to see my time reserve. So we have first relation between copies is there when one copy lies inside the other, yes? And if you have two copies, we have some copy which contains both of them. Second relation between copies we'll discuss later is whether they intersect or not. Yes? I will discuss it just a little later, but first of all I need to look at some point. Yes? It is contained in the whole K, right? At the same time, it contains in some copy of the first order, yes? Then it is contained in some copy of second order. Then it contains in some copy of third order. So we have, for each x, we have a sequence K I1, and it contains, x belongs to all these copies. It contains K I1, I2, it contains K I1, I2, I3, etc., etc. And this sequence is infinite, right? There will be an infinite sequence of diminishing copy, nested copies containing one point x. Yes, so that their addresses form such a growing sequence. Right. Then x is just the one point set x is the just intersection of all these copies. Right? Because you see the diameter of this copy is less than q multiplied by diameter of k. And the diameter of this one is less than q squared, well, q maximal. I write just q. Q squared multiplied by diameter of k. And on the n stage we'll have ki1 in. Its diameter will be less than q to the power of n multiplied by the diameter of k, so the diameter tends to 0, right? And we have a nested sequence of compact sets whose diameters tend to 0, and their intersection is just one point. It is non-empty, and this is a unique point x. So x is the intersection of all this I1, In, and it has an address. Each copy has its address. Why not the point? The point also should have an address. And the address of the point will be this sequence. So address of x will be I1, I2, I3, etc. It's very interesting. So copies have addresses. Is it possible that a copy has one address? Yes, of course. For example, if I take 1, 1, 1, 1, 1, 1, 1, 1, I will get this point, right? Or if I take, so for any sequence I will get the point. But really, let us check what kind of addresses we have. This address is 1 in the period, yes? This address is 2 in the period. This address is 3. And what is the address of this point? It is 2 and 1 in period and 1 and 2, yes? So there are points which have multiple addresses because they lie in the intersection of two copies. So if a point lies in the intersection of several copies, it has several addresses. Then it is rational to consider the set of addresses. Okay, so we'll do the following thing. First we consider the set. So if we have a system S1, Sn, we consider the set of indices I. It will be 1 to m, right? So if we have S1 and Sn, we have fixed the system and consider what rules are governing its attractor. So first rule, that all addresses are taken from this set of indices, yes? Then if we have I to the power of n, it will be addresses consisting of n symbols, yes? N symbols, beginning from 1, 1, 1 and finishing with m, 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 and all between them, right? And the set of all finite addresses will be I star. It will be the union of all In. So I star is the set of all possible addresses of copies, independently of their order. So we have different copies and different addresses. And then I will consider the infinite addresses, strings. So it will be the set of all infinite sequences I1, I2, In ad infinitum, right? such that all ik belong to I. So each point has an address from this set. Each point has an address for this set. It is interesting, how can we find the distance between addresses? We can define the distance between addresses. But first, I need to define the map pi from I infinity to k. If we have an address, each address defines unique point, right? So for each address, we put into the correspondence some point of k. Each address defines unique point, but for a point we can have even an infinite set of addresses. It is possible. Okay. So we have this map pi can be considered from metric point if we define a metric on the set of addresses. How to find the distance between two addresses? Suppose we have some vector r, which is r1, rm, some number, all rk are less than 1. So we have some vector r. And suppose we have some multi-index, sorry, I1, IN. It will be denoted by boldface I. Then we define r to the power of I. R to the power of I will be Ri1 multiplied by Ri2 multiplied by Rin. Okay? To each multi-index we put into the correspondence such a composition of then, and if we have two addresses, alpha 1, alpha 2, alpha 3, etc., and beta 1, beta 2, beta 3. Then we can define dr of alpha beta. It will be r to the power alpha wedge beta. Is it complicated or it is simple? It is simple because it is simple. It is complicated because we are soon finishing our lecture. Yes, it is. So you understand what it means. For example, if I have 1, 2, 3, 1, 2, 3, 1, 2, 1, 2, 3, etc., and if I have 1, 2, 3, 1, 1, 2, 3, 1, 1, 2, 2, 3, 1, yes? So this is a periodic, and this is also periodic sequence, right? It will be alpha, it will be beta. So r to the power alpha wedge beta will be R1, R2, R3. You understand? Okay? Please, your questions. So if we have two infinite sequences, we take their longest common prefix, yes, and make a composition of this R case corresponding to this prefix. Yes, for example, the so 1 2 3 1. Yes, yes, yes. Okay, sorry. So this will be the distance between infinite strings, between addresses. How many minutes I have?
If you want, you can finish.
Huh?
If you want, you can stop now. If you want, you can stop.
I don't want to stop. I want to know my fate. Time is over. But okay, so I will say just one thing, that yes, I will continue on the next lecture. Yes. Thank you for your patience. Yes, and for this very hard toil of listening to this, all this. I hope that next lectures you will enjoy much more. What, please?
Which book? Book. Textbook.
Oh.
We will provide you.
Yes, there are several books. There are many books, many papers, and different arrangement of the same topics.
Yes.
Because these are basic topics, and so I can give you a list of books, beginning from Hutchinson's paper and others and others and others. But to choose the best one, it is your right.
If we consider infinite construction map, then
What?
if we consider infinite construction map, then is there always exist a attractor?
If we have a system, infinite system of contraction maps, it's a more subtle question, because we can organize very ridiculous infinite system of contraction maps. Yes, because you see, we'll have so if you need some rest, you can go, but I will explain the answer to my question. Suppose you have infinite system S1, S2, and yes, and we have some k, right? Then we have S1 of k, union S2 of k. This will be the infinite union, right? And if we have a finite union, it will be compact. If this union is infinite, it is not compact. There will be additional points, right? For example, you can take unit interval, yes, and find some closed some system of closed intervals which do not intersect each other, yes, and whose union is dense in this, then this union will be, this definition of attractor must be changed, because in that case we need to have a closure of this union, yes. But there may be many paradoxes when we consider infinitely generated systems. Yes, from one point of view, I like these paradoxes because I made such infinite examples even in somewhere about 1977. From the others, I try to avoid them.
I think just we prove of the finite case we use the maximum of Qi. So here infinite case maximum of Qi
Well,
equals to
C
1.
primum. No, we will need then, for example, we can consider the case when the sum of all QA is less than 1. So if they form a converging series, yes? You are free, I am just explaining, so you have a break. So it will be one case. But even if the sum, I can make a family of mappings whose contraction ratios, the sum of contraction ratios of these mappings will be less than 1 divided by 100, yes? And the attractor will be the whole interval. Because we can make very small intervals, segments, which form a family which is dense in the unit interval. So there will be different laws for infinite systems. Please, your questions. This is the best dish.
Questions after lunch, because we have short time after for lunch.
Ah, yes, we have a lunch,
Yeah.
yes. Oh, yes. I,
Meantime, you can think while eating.
yes. Okay.
So I just want to announce that we prepared one kit, but there was some problem in die preparation, so that's why we did not distribute to you today. And I asked again the vendor to formulate all the things and distribute tomorrow. But I have some notepad and pen so that you can use it. Okay. And we will assemble here at 1:45. So all of you please go and have lunch. Okay, 1:45.
So is it
We will meet at 1:45.
at 1:45?
Yeah. So you just go, take lunch, and come back.
And come where?
Here. अभी ऑन है, ऑन है। बेटा लगाना जल्दी से, कनेक्टेड है। So today we are going little delay. Eh? So tomorrow onwards we will see that we stick to the times. Eh? तभी मैंने बोला था ना कि उनका लगा रहता ना लैपटॉप सर का। हैं? सौरभ को बुला लो, मोहित। आपको आता है? देखो कुछ देखना जरा। यस सर। Can I connect to your laptop?
What?
Can I connect to your laptop?
Yes.
Because you have that notes. अरे ये हटा, मेरा हटा दो इसको, लैपटॉप को। हैं? बेटा मेरा निकाल देना लैपटॉप, इधर रख देना। सर वाला लगा लो आराम से, ठीक है। बनाने दो इसे, बनाने दो। लगा दो, डायरेक्ट लगा दो। कैसे लगाता है?
नहीं डायरेक्टली ये लगा तो दिया
इनके पास तो फ्री टाइम है हमारे पास, डायरेक्टली भी आ जाएगी।
चलो चलो लगा रहे हैं, कोई नहीं।
इसके साथ कनेक्ट नहीं
आप मेरा वो कनेक्ट करो, पीडीएफ निकालो मेरा। I am working as an assistant professor here. So before that I have done master from IIT Kanpur and PhD from IIT Madras. So now I am going to take your second lecture of this GIAN course, and sir will discuss these things more in detail after my lecture will be over. So we were going to discuss the Cantor set, and now you can see the picture here. So generally we take like 0 to 1, and we remove this middle third part. We remove this middle third part, then what we will get? We will get 0 to 1 by third, then 1 by third to 1. Okay. Then again divide the middle third part, then what will you get here? Anyone? Yes? 0 to 1 by 9, then 2 by 9 to 1 by 3, and this side what will you get? This is 2 by 3, 2 by 3 to 7 by 9, and then 8 by 9 to 1. Okay, so we do this indefinitely, then we will get the Cantor set. Okay, so here the simplest self-similar set is the Cantor set, means easily you can find, and usually then the second point is saying that it is defined by the system S1 x is equal to x by 3 and S2 x is equal to x plus 2 by 3 on the real line. So sir will take the tutorial after this class, then he will show you that if we use IFS tile, so we have one programming software package, we will use IFS tile. In IFS tile we use one program, in that we use this thing k is equal to 1 by 3 into 1 is scale by 2 comma 0 into k. Okay, and then we will see that S1k intersection S2k is 5. Okay, what is S1k? K is here 1 by 3 into this thing. S1k, S1x is x by 3. So you find S1k. Then find S2k. So how will you find S1? Suppose S1x is what? X by 3. And S2x is x plus 2 by 3. Okay, so now you can see that where S1 0 is going, it is going to 0. Okay, and like the point is there 1 by 3, 2 by 3, each point you can see where they are going and mapping. So same way you can find S1k, then find S2k, and if you will find the intersection, then you will get the empty set, then the set k is totally disconnected. So who will tell the meaning of totally disconnected? Anyone in the class who can tell? Anyone can give the example of any totally disconnected set, or any example of connected set? Anyone? What is the definition of totally disconnected set? Yes. So what is the definition of totally disconnected set? If it does not contain any connected subset with more than one point. Clear? So any example of connected or disconnected set? Another example? Set of rational numbers. What can you say set of rational numbers? Disconnected or connected? Set of irrational numbers. And set of integers. Okay, so you got the idea? You got the definition of disconnected set also? Yes? Any doubt in that understanding this thing? Okay, then I will go further. So who introduced this? What is the history behind the Cantor set? So now you see the first picture, it is Henry J.S. Smith. Then the second picture is Emile du Bois Raymond, and the third picture is both the pictures for Cantor? I think last one for the Cantor. The last one is for the Cantor. So this set was introduced in 1874 by Henry J.S. Smith in his paper on the integration of discontinuous functions. So you already know what is the meaning of discontinuous function. Any example you can give for discontinuous functions? What will be the examples for continuous functions? Trivial examples. Polynomials, rational functions where denominator should not be and trigonometric functions. Any trivial example? Constant functions are continuous function. Identity function, they are also continuous function. Any example for discontinuous function? We can piecewisely define and like that. Okay, so you can know the definition of discontinuous function. So in 1874, Henry J.S. Smith wrote the paper Integration of Discontinuous Function, and he introduced this Cantor set. So in the morning session also we were discussing that those things were known, fractals were known, but we were not calling them fractals. Like nowhere differentiable functions were there. It was like Weierstrass function as Takaji function. Okay, but we were not knowing that they will be the fractal objects. Means when Mandelbrot came, okay, after that many researchers followed by him. So finally it was used by yes. So second one is this Raymond here, and third one is Vito Volterra. Then fourth one is Cantor. So finally it was used by Cantor in 1883 as an example of a perfect nowhere dense set on the real axis. So what is the meaning of perfect set? Who will tell? What is the meaning of perfect set? Or it is given here nowhere dense set. So what is the meaning of perfect set? Who will tell? Perfect set. So what is the condition on perfect set? Like Swati is there, Vansika is there. I taught them real analysis for master. Swati, can you tell what is the meaning of perfect set? Or Vansika? Yes. Closure must be equal to the same set. And what is so that means the set must be closed, and any another property? Set must be closed and contains no isolated points. Can you give any example for that? Cantor set is one example you are getting here. That is a perfect set with measure 0. Okay. So what can we say about the set of natural numbers? Or any finite set. If you take any finite set over R, any finite set in R, okay, let us say I take example 1, 2, 3, 4, then okay, so you take any point 1, make a neighborhood, then it will contain 1 itself, not other points. Okay, so 1 is isolated point, 2 is isolated point, 3 is isolated point. Each point of finite set is a isolated point. Same for the, means you generalize here set of natural numbers. So natural numbers also, each point of set of the natural numbers are the isolated points. But here what we are saying that perfect set means it must be closed and no isolated points. So this Cantor set is having this property that they are perfect set. And what is the meaning of nowhere dense set on the real axis? Anyone? Nowhere dense. Correct, something like that. Okay, so nowhere dense, it is having the property. Then it is the attractor of a system. So I think sir has taken class, he was discussing these things. Okay, so you take some notation here is S1 comma S2 in R, and already we discussed that S1x is equal to x by 3 and S2x is x plus 2 by 3. So now, like I was telling you here that S1 of 0 is where S1 of 0 is going and where S1 of 1 is going. Okay, same way you can see that S1 of 0 comma 1 is mapping to where? This whole interval S1 is mapping here, right? Okay, 0 to 1 by 3, and the whole interval is mapped to here by S2. Yes, 2 of 0 comma 1 is going to 2 by 3 comma 1. Okay, so here k is any subset of 0 comma 1 and the copies k1 and k2, okay, they are disjoint. So k1 and k2 are here, k1 and k2 are here and they are disjoint. So by Harta's theorem, okay, so anyone heard about Harta's? Huh? So there is a person, his name is Masato Hata, and he has done many works on dimension theory of self-similar sets. And so Hata's theorem is, I just write here so that you can relate it nicely. So I just write here. So it's saying that a non-empty compact metric space, a non-empty compact metric space is totally disconnected, if and only if it can be written as the inverse limit, it can be written as the inverse limit, it can be written as the inverse limit of a sequence of finite discrete spaces, Okay, so as I have written in the last line of my presentation, that you apply the Hata's theorem, then what will you get? The set K will be totally disconnected. Okay, then I move further, one slide further. So though each perfect totally disconnected set in R to power n is homeomorphic to the Cantor set, so here whatever I am writing, you all of you try to follow and try to take them as a challenges, and when you finish your classes today, then you go and try to solve these things. Okay, and if you have any doubt, then tomorrow we will discuss more on these things. Now I am going to discuss, yes, so what can more you say about the Cantor set? Or the Cantor set is uncountable? Cantor set is uncountable. And what is the fractal dimension of Cantor set? Anyone? Anyone is knowing? Fractal dimension of Cantor set? It is log 2 by log 3. Okay. So do you know how to calculate this? Anyone is knowing how to calculate it? Okay. So what is the dimension formula? Dimension formula. Okay, I am following this from Barnsley book. Box counting dimension limit epsilon tends to 0 log of n epsilon divided by log of 1 upon epsilon. Okay. So what is the fractal dimension for Cantor set? It is log 2 by log 3. For this Cantor set, dimension is log 2 by log 3. Okay, so you know that means if you take epsilon is 1 by 3, like here it was full interval 0 to 1, okay, and in first iteration you want to cover this one and this one, okay, then epsilon is 1 by 3, you are taking epsilon is 1 by 3, here also epsilon is 1 by 3. Then how many boxes you need to cover these two things? How many boxes you need? 3. You need 2 boxes, right? This one and this one. So n epsilon will be 2. Number of boxes needed to cover these things and these things 2, and epsilon is 1 by 3. Now if you go further, epsilon is now 1 by 9. Then how many boxes you will take? So like you will write D is equal to log of how many boxes you are getting? 4, right? And epsilon is your 1 upon 9. Epsilon means second iteration. Epsilon is 1 upon 9. Then this will become log 9. Then what you can write? You write log 2 square divided by log 3 square, then this 2 will go out, okay, and this 2 will go out, then again you will get log 2 by log 3. So means by any number of iterations you go, and if you will calculate the fractal dimension, box counting dimension, then you will get the answer is log 2 by log 3. So fractal dimension of this Cantor set is log 2 by log 3. And like in previous slide we have discussed that the Cantor set is composed of two smaller copies of itself, okay, scaled by a factor of 1 by 3. So that's why they are self-similar objects, okay. So now sir will show you after this in programming part. Now we are going to see Antoine necklace, and it is the attractor of a system, some system S1, S2, Sn of contracting similarities, and each Sk tending a torus T to a torus Tk subset of T, such that now you can see here, and this is so though this set A is totally disconnected like we have seen for Cantor set, and any loop K that is interlocked with the necklace cannot be continuously shrunk to a point without touching A. So after this my lecture will be over, then we will zoom it and we will rotate it in the programming part, and we will show you that what I want to say here. Okay, so this is another figure of that thing, and both the figures made by different programming, means one is made in IFS style and another is made in fractal tracer, and in tutorial session we will discuss these two things, that means what is the programming part behind that. So though this set A is totally disconnected, any loop K that is interlocked with the necklace cannot be continuously shrunk to a point without touching A. So this is one property, that they cannot be continuously shrunk to a point without touching A, right? So I just go more further. Yes. So now we will discuss another. I think I have to. Now it is visible, clearly visible. Yes. So like first we have discussed Cantor set, and Cantor set we have discussed all the properties, that is a perfect set and measure is 0 and it is totally disconnected, uncountable, fractal dimension is log 2 by log 3, and what more? It is having self-similar structure or property. Now I am going for this is Koch curve. So it was introduced by Swedish mathematician Van Koch, and he introduced this in the year 1904, and in the paper entitled On a Continuous Curve Without Tangents Constructible from Elementary Geometry. So you can download this paper, and after downloading this paper you can see that what he has written in that paper. So I just want to say something about this Koch curve. So now you can take means those who are new here, like some students are here from BTech or MSc first year, they are not having the idea of these fractal functions. Okay, so like you have this means this is a triangle kind of shape, you can say. Okay, so whenever you are getting any like in Cantor set, what we are doing, this was 0 to 1 and we are removing the middle third. Okay, so here what we will do, wherever we see any line or segment, what we do, we just add something to that. Okay, like this. So this is our first iteration. This is our first iteration. And next iteration means we started with this. Okay, so this is your first iteration, and now we will go to second iteration. So wherever you are getting a straight line or any segment, you do the same thing, repeat. Okay, so what will you get here? You will get this one. Here also you have to do like this one. Then here also you have to do like this. Then wherever you are getting, you have to do like this. Okay. So you are seeing I am constructing this part. I am constructing this part, okay? And now, like sir will tell you in next lecture that, like in this lecture also we will say, okay? So what you are observing here? What you are observing here? In second iteration, third iteration, the perimeter is increasing, but the curve is enclosing the finite area. Okay, means when they observed this property of fractal objects, then it was a great property, right? Means the perimeter is increasing, it enclosing the finite area. So now you see here, means when you increase the number of iterations, then you will get this type of Van Koch curve. And if we will go further, now you see here. So like for Cantor set we have chosen two mappings, S1 and S2. To construct this, we are taking S1z is equal to z by 3, S2z in this way, S3z in this way, and S4z in this way. Okay? And you can see here means K1 and K2. K1 and K2, they are having one point common. In Cantor set, what you have observed? They are not having anything common, right? But here they are having one point common. Okay? So yes, so we can go to another object, and this is Sierpinski gasket. And already you know that how to construct it, and those who are new, for them I can tell them that you take one triangle, and you can take 0 1 0 1 like that. Okay, and what you do, remove the middle third, remove the middle third, like that you remove the middle third. First iteration will be triangle was given and remove the middle third, and wherever you are seeing the triangle now, do the same thing. In the second iteration, what will you do? This is the triangle here, this is the triangle here, and this is the triangle here. So what you do? Again remove the middle third, again remove the middle third. Here also you again remove the middle third, and again remove the middle third. Okay, now there are many, right? So again what you do? Same process you apply. So if you go to increase your number of iterations, then you will get this type of result. Okay, so this is called Sierpinski gasket or Sierpinski triangle, and is the most typical example of self-similar set. Like Cantor set was the first example, then this is the second example, self-similar set, and it is widely used as a most convenient illustration of self-similarity. And it was presented by Sierpinski in February 1915 as an example of a curve which is ramified at every of its points. So who will tell the meaning of ramified? Anyone who can tell the meaning of ramified? Huh? So ramified means branched or divided into branch. Huh? So I just go next slide. And next slide, the picture of the person Sierpinski in 1928, and then we see that like in previous slide I have said that example of a curve which is ramified at every of its points. So now we will see here it was constructed. So now you see 3 lines, and for the timing you can ignore the arrows. So it was constructed as a limit of a sequence of polygonal lines shown on the right side. Okay, so we'll see how we are going to construct that Sierpinski gasket or Sierpinski triangle by the sequence of polygonal lines. So now you see here, so first iteration, then are you able to relate? Okay, so you keep on doing this thing. So I just go back and you see the first iteration, then here, and then here, and keep on doing this thing, then you will get this one. So as I said that it was constructed as a limit of a sequence of polygonal lines shown on the right hand side. So how to choose the mappings here? So it is the attractor of a system. You take 3 mappings, S1, S2, S3. Like in Cantor set you have taken 2 mappings, S1 and S2. So here 3 mappings. And where this mapping, how will you define the mapping? Mapping will be skx is equal to x plus ak by 2. So where ak are the vertices of the triangle. And now if you see here what they are having, like this portion and this portion are having one point in intersection, and they are having one point in intersection, like here also one point in intersection, right? So they are having single intersection property, like in previous figure also. In previous figure 1 curve also they are having single intersection property, because the intersection of the copies ki intersection kj, in this you are seeing the middle point, right? Middle point means if you say if you take 0 to 1 and 0 to 1 here, then this will be the middle point. Okay, but you take any kind of triangle here, you can take any kind of triangle here, then the middle point will be ai plus aj by 2. And the last property causes the topological rigidity of Sierpinski gasket. So any continuous injecting map of Sierpinski gasket to itself is a similarity extending like this Sierpinski gasket. SG means Sierpinski gasket here to one of its copies. Okay, so what is the meaning of this similarity? Anyone is knowing about similarity? Contraction mapping? Contraction mapping? What is contraction mapping? A function f from x to x on a metric space is said to be a contraction mapping if d of f of x comma f of y less than r times d of x comma y, and r must be lying between 0 and 1, and if this less than will become equal to, okay, d of f of x comma f of y equal to r times d of x comma y, where r lies between 0 and 1, then that is a similarity. So now we are going further for the Levy curve, and the Levy curve was first described and analyzed by Ernesto Cizarro in 1906 and George Favre in 1910, but now bears the name of French mathematician Paul Levy. Like in previous also when we were discussing about Cantor set, then before Cantor 3 mathematician came, and then one mathematician introduced the Cantor, but who was get the name Cantor. So here also the Levy curve was first described and analyzed by Cizarro, and then 1910 by George Favre, but now bears the name of French mathematician Paul Levy, who was the first to describe its self-similarity properties in 1938. So now by this you can see that means someone started in 1906 and someone has added something on 1910, and someone thoroughly done the research in 1938. So now you can see the research gap. So means whenever you are going for PhD, then you don't think that in 1 or 2 years you will be able to do very great work, but you try hard to get your results. So now you see here the Levy curve will look like this, and here we see that two maps here. So Levy curve is the attractor of the system. Two mappings we are taking here, S1Z defined in this way and S2Z defined in this way. So Paul Levy proved that this curve tiles the plane. So we will going to learn these things, that how these self-similar objects are tiling, means tiling the plane, and they are filling the space. So for that I just show you one more slide here. Now see here you have taken one triangle, and triangle with the vertices 0 and 1, and this midpoint is 1 plus I by 2, and the action of the operator. So I told you in previous slide that S1Z is 1 plus I by 2Z, and S2Z is given here on the first slide. Now you start applying these points of triangles, all the points, okay. Then take with union, S1A union S2A, the mapping T. Then you will get this thing. This is
We take 4 triangles and apply this transformation to each of them.
then you will go to next.
Yes. So go down. Yes. So if we take this triangle, then taking 4 such triangles, we'll get the square.
Yes.
Yes. And this square tiles the whole plane. You see? By all these boxes.
Yes.
And then we apply this transformation.
Again and again
No, to each triangle.
to each triangle. Yeah. So that one triangle divided into 2.
The next.
Yeah. Next slide. Yes.
Next frame. You see, we took this triangle, red triangle, and
Apply the maps.
by these 2 small red triangles.
Rectangles. Yes.
We took yellow triangle, which was here, and we replaced it by 2 this triangle.
Yes.
And the same thing was done with this rose triangle and
Other color.
blue.
Yeah. Blue one.
Okay. So this new figure will also tile the whole plane.
Whole plane. Yes.
Without overlapping.
Yes.
And
So
we repeat.
yeah. So we repeat. Now you see. So repeating the transformation at each step, we obtain a figure, this figure of the same area that tiles the whole plane. Then we keep on doing. Then again you see nice shape and structure here, and this is also tiles the whole plane. And so repeating the transformation at each step, we obtain this figure of the same area, and that tiles again the whole plane. And we are going more further. And so the limit of AK, what we defined previous slide, is the union K4 of 4 symmetric non-overlapping images of K, which has the same area and tiles the whole plane. Now I will close my slides after some time. Then we will see the programming part, and sir will try to rotate all the figures and zoom the figures. Then we can have a clear vision of these things. Then here see means the figure. In this slide we want to magnify. And see that what is happening here. So when you magnify the set K, we discover the open domains contained in K. So what are these open domains? And sir was discussing about one paper where the person have 16 types. He discovered the 16 types of open domains contained in K. So here you can count, they are the 16 open domains, and one can see them in the complement of K2. Means these are showing the 16 open domains contained in K, but complement of K2 contain these types of open domains. Then, thank you. So, sir, now can you come and show the means that how to rotate, and after that we will take break. After showing this we can have break.
And what I have to show?
These figures, if you tomorrow you are showing me na rotating and all these things.
Yes. Really, I didn't understand what I have to do.
You have these figures in your programming.
Yes, yes. Oh, okay,
just-
okay, yes. Okay. One second. Yes, yes. 1 second. Sorry. Open. Okay. I forgot where it is. Yes. Escape.
Just give 5 minutes, 10 minutes break. 5 minutes break.
Don't worry, I will find everything. Oh, it is here.
Yeah.
Oh, okay. Okay, so let us come to this Levy curve. So you see this one, all right? Okay. Okay, so this is
We
the
were
Levy.
discussing about this Levy curve.
Yes. And if you wish to magnify it, you can do this. Yes.
So when you magnify, then you will get this one.
Yes. So we will have these spots.
This is spots, yes.
You see, this is a completely blue spot.
This is completely blue.
Yes, and here is the spot of the other type.
Other type also completely blue.
Yes. And if you look at the complement, since the complement is covered by shifted images of this Levy curve,
Yes.
then in complement you see this
Open domains.
also, yes.
Yeah.
So there are holes of the
Yes.
same form which will be covered again by this. And here it is this picture, we
Correct.
discussed it, yes. And this is also discussed, and then all these things already
Yes,
have
yes.
been discussed.
Yes.
So we can
Here
just,
also we can zoom, yes.
yes. If you magnify it, then you will have a lot of pleasant
Yeah,
pictures.
you can show that necklace also.
Oh, yes.
Rotate and see.
1 second. I will show the necklace.
Yes. So
Yes, it was promised that we will rotate this
and-
necklace. Yes. No. I will change this. You see, it can be rotated.
So this was figure like this one, right? But they are not intersecting. Okay, they are not
Yes.
intersecting. Okay.
Yes, its problem of rotating is
So
sometimes it
you can
rotates,
see,
sometimes it rotates. It rotates around some distant point.
yes.
Because it is some difficulty with rotations in 3D. Tools rotate again. Zoom box.
So we can zoom some part also, and we can see, means it is appearing that they are intersecting, but they are not intersecting.
Yes, it is possible, right. Let me try to rotate. Oh, it pans it. Instead of rotating, it pans.
Okay.
Okay, let me return to the initial stage, and no, it depends. It depends, and oh yes, now it is rotated.
Yes.
Okay. So you see, in dimension 3, it takes some time
Yes.
to. You need to relax and enjoy, and then you see the result. Yes. Okay.
So we will discuss these things, how to make changes in the tutorial.
Yes.
Yeah, you can show this Menger response.
Menger, oh, yes.
Yeah. So we have another figure. I did not add in the slides.
Yes.
You can see here.
We didn't discuss it, but it is very famous because it is a universal curve.
Yes.
Every one-dimensional set can be embedded into Menger sponge. So it is, and this is also very
Also
good
one,
things. It's just a fractal square, which is a Vichek set. Yes, and maybe this one can be built later. Oh, sorry. What it is? Oh.
Yeah.
So this way and
Again
this way again.
So we will learn these things in the tutorial.
Yes.
So that will be interesting.
So and now we can finish.
Yeah.
Right?
So now you want to take your lecture now, or you want some break?
Break, of course.
Break.
So,
5
of
minutes,
course.
10 minutes?
Oh, 15.
15 minutes? Okay, so
Yes.
there is a break for 15 minutes.
Okay.
Tea? Okay.
when we considered this address space on the set of addresses, we defined dr of alpha beta will be r to the power alpha wedge beta, right? Where this means the maximal common prefix of these two infinite addresses, and this means that so I will remind it, if r is r1 rn and alpha wedge beta is I1 In, then R to the power alpha wedge beta means R I1 multiplied by RIN. Yes? So we introduced this matrix on the index space, on the space of addresses. And we have a map which sends the address to the point X, which has such an address, right? Okay. So what happens if we introduce such matrix? So it is very interesting. So if we have space of addresses, so we have alpha 1, alpha 2, beta 1, beta 2, beta 3. On this space of addresses, we can introduce the operation. So if we have alpha, and we have some index I, then I alpha will be I alpha 1, alpha 2. So this map, I will call it sigma I. Sigma I is the map which puts an index I in front of the address. What does it mean? So if you have a self-similar set and we have its copies K1, K2, K3, and we take some point, and if we add to the address of this point a number 1, it means that we apply the map S1 to the address. Yes? So P of I alpha will mean Si of pi of alpha, right? So if this point is pi of alpha, so this point will be pi of 1 and then alpha, right? So then the set of addresses I to infinity, we denoted it by I to infinity, is the union of, here we have I is equal to 1n. If you have indices from 1 to n, then I infinity will be union of 1, then I to infinity, union 2, sigma 1 of of I to infinity, then union sigma 2 of I to infinity, and union sigma m of I to infinity. It means that each infinite sequence begins from one of these numbers, 1, 2, or m, yes? And the space of all sequences beginning from 1 will be just this one. Okay. So, I to infinity looks this way, but what does it mean? Suppose we have the matrix dr on I to infinity, yes? So dr of alpha beta is r wedge r to the power wedge alpha beta, right? Okay. For example, if we have two elements alpha and beta and apply the map sigma I to alpha beta, then we'll get two addresses, I alpha and I beta, right? Yes? If you have two addresses and we write in front of them the same number, then we'll have two addresses which are quite long. But what can we say about this distance? So dr of alpha beta is r to the power of alpha wedge beta, right? Yes? And dr of I alpha I beta is r to the power I alpha wedge I beta. It means the common part of these two indices became 1 there, and therefore it is Ri multiplied by dr of alpha beta. So, what happens? These mappings are similarities, yes? In the distance dr, these mappings are similarities. And the index space is a complete metric space. And this complete metric space is union of these images and the similarities. So what we have a self-similar complete metric space with coefficients Ri. With Lipschitz coefficients Ri. Wow. So, but it is very interesting space. It is totally disconnected, perfect. Do you see? You see? Let me check it. So I infinity is the set of all possible A1, A2, of all possible sequences, right? And it is the union of 1 I infinity, then 2 I infinity, and m I infinity, right? And these sets are closed, right? They are closed and they do not intersect. So I infinity is the disconnected union of sets I infinity, yes? So this set is totally disconnected, perfect, and it can be projected from to this space K. Then if we have pi of I infinity will be sent to Si of K, right? So we have this set I infinity, it projects to K, and its copies are projected to the copies of K1, K2. Yes, and if we supply I infinity by the matrix with coefficients Q1, Q2, Qm, yes, so this projection will be Lipschitz. It will be Lipschitz because diameter of I infinity is 1, diameter of K is, we don't know what it is, but it is the diameter of K, therefore it will be diameter of K Lipschitz. Okay. And now we can consider the connectedness properties of the set of self-similar set. So we have a projection of I infinity to K. You see, I infinity is the infinite product, is an infinite product of 1 n to the power of infinity, right? So it's the infinite product of discrete, compact finite discrete spaces. Yes. Okay. And and it is totally disconnected, therefore we have the following theorem. So one second. So suppose we have a compact set K. Suppose K is the attractor of system S1 Sm. Consider its copies. Its copies are K1, Km. For these copies, we can consider their intersections. Yes. And we can construct the intersection graph of K, whose vertices will be copies, and the edges will connect these vertices is if K1, if respective copies intersect. Okay, for example, if you have a Sierpinski triangle, yes, we can consider the intersection of copies, K1, K2, K3, yes, and each two copies intersect in one point, therefore we can draw the intersection graph. It will be K1, K2, K3, and there will be three edges connecting these vertices. Yes. So this intersection graph sheds some light on the connectedness of the attractor. 1 second. First, if the attractor, if for any ij, ki intersection kj is empty, then k is totally disconnected. How to prove this? For example, if you have this one, if any two copies have an empty intersection, then the attractor is totally disconnected. So consider the projection I infinity to k. Consider the projection I infinity to k. One second. Yes. Please notice that pi in this case is a continuous bijection, right? How do you think? So consider the projection of I infinity to k. Each point in k has unique address because the copies do not intersect. Yes? Each point in k has unique address. Therefore, this map from I infinity to k, first, it is continuous. Yes, because if we consider this matrix, it is Lipschitz continuous. Second, it is one-to-one. I infinity is compact. A continuous bijection of a compact space to compact space is a homeomorphism. All right? So, a continuous bijection of a compact space is a homeomorphism. If you allow me, I will prove. So suppose we have some continuous function which sends k1 to k2. k1 and k2 are compact spaces. Yes? Since k1 is continuous, k2 is continuous too. Okay. Right? What? Compact, yes. F of k1 is compact. Then, if we have for any closed subset of k1, this closed subset is closed or is compact. So its image f of a is also compact, so it's closed in k2, right? So this bijection sends closed sets to closed sets. Therefore, it sends their complements, open sets, to open sets. So the inverse map is also continuous, yes? Therefore, this map is a homeomorphism. So a continuous bijection of a compact space is a homeomorphism, yes? So K is homeomorphic to I infinity, but I infinity is totally disconnected. Therefore, K is totally disconnected too. So if copies do not intersect each other, then the attractor is totally disconnected. Second property is the following. Each self-similar set is perfect. means it doesn't have any isolated points. Oh, not very each. There is one possibility when a self-similar set is not perfect. If it is one point, if it is a singleton. In other cases, so let K be the attractor of the system S1, Sm. Okay, is the attractor of such system. So if the fixed points of all these S1, Sm coincide, then the attractor will be a single point. Another case, if some two fixed points do not coincide, then the attractor will be a perfect set. Okay. How to prove this? So I need to change the formulation. Yes. If there are Si, Sj such that fixed point of Si is not equal to fixed point of Sj, then the attractor K is perfect. Is a perfect set. We can prove it by a contradiction. Suppose K has an isolated point. So let us consider the projection of I infinity to K. This projection is continuous, yes? And K contains an isolated point. So consider the K, and it has an isolated point, right? So each neighborhood of this isolated point consists, sufficiently small neighborhood of this isolated point consists only of this point. So this point is an open set. So consider its preimage in I infinity. Consider preimage of this set. It will be this preimage will be a open set in I infinity. So it will be can be represented as union of images of I infinity on the sigma I1 In, right? Therefore, it turns out that for some Si1 In, SR1 or IN is a point, therefore K is also a point. K is also a point. Therefore, K is a perfect set. Third, I need to correct this slightly, correct this proof, but I need some time for corrections. Sorry. So one more important property of self-similar set is the following. So if you have a self-similar set and if we have a point, then we need to find the fundamental system of neighborhoods of this point. Let x be a point of K. Put V rho of K, or maybe I need to use different letter. Let be a W rho of K of X. Be the union of all K I1 IN such that K I1 IN contains X and a diameter of K I1 IN less than rho K I1 IN is less than rho and more than rho Q minimal. Okay. So the number of such multi-indices for which X belongs to KI1 IN is maybe sorry. Maybe I will write it in slightly different manner. It will be a union of all K I1 IN such that diameter K I1 IN less than rho and diameter of K less or equal than rho and KI1 IN minus 1 is greater than rho and KI1 IN contains X. So we take a point X and consider all this for each address of the point X. We have a copy of some order whose diameter is less than rho and contained this point. So the number of such copies should be finite. Therefore, then W rho of X is a compact neighborhood of x in K, and its diameter of diameter less than 2 rho, less or equal than 2 rho. Yes. Okay. So if you consider all the compact sets, all the copies which contain the point x and whose diameter is no greater than rho, then the diameter of this union will be less than 2 rho, right? Okay. Thus the set W rho of x, for example, rho equal to 1 divided by, for example, to cube divided to the power of n, yes, where n goes from 1 to infinity, is a fundamental system of compact neighborhoods of x. Fundamental system of hoods of x. So now we can proceed. Can we make a short break? Okay. So I need to find my language is adapted to the needs of those who is programmed. So I will explain to you. So IFS, a file for this program is consisting of blocks. So each block begins. So to make the IFS file, we just write some kind of program and in some text editor. For example, if you have Notepad++ or something like that, it will be good to write such program. So maybe I will, yes? Which? Oh, this way. Okay. Yes. So how an IF style program looks like? It looks the following way. It consists of blocks and blocks have names. So it's a CAD code. How to write it? CAD code. CAD code and some name. It will be a name of block. Yes. So it can consist of independent blocks, and these independent blocks give different fractals. Yes? But also it can consist, it can contain parent block, or how to write this way. It contains a parent block, yes? For example, here is parent block, and it can contain dependent blocks. For example, you can write some letter A, and it refers to D. Then if we define some numbers, some variables, and some operators in one block, then they are inherited by the dependent block, so you can use them later. It is very convenient because you can make find some fragments and...
Sir, have you started a tutorial? Coding. We have tutorial in PG Computing Lab.
At which time?
We have 10 minutes break for tea, and we were supposed to start at 2:45.
Sorry, I can look. Please guide me when I need to stop and when.
I am just asking, have you started tutorial?
You mean tutorial in a computer lab?
Yes, tutorial was scheduled in computer lab.
At which time it can be opened?
It is opened, but we have tea break before that.
Yes.
Just to start. The break is just to start at 4. We are starting
And
break. Now it is 3:56.
So
We will start tutorial at 4:10 or 4:15.
at 4:15.
Yes.
Okay.
Yes, sir.
This is very good.
Everyone can. Sorry.
This is very good because I need some time to collect my thoughts.
You also take your time. Your tea is also coming.
Oh, thank you very much. So I can switch, but you see there is a problem. 1 second. There is one problem. I need to explain some things on a large board.
Yes, sir. We have projector there.
Projector or
We can connect our laptop. Everything will be displayed on the lab itself.
so it will be just a projector.
Yes, yes. Board, green board and white board is also there. We can
Why?
use
I can write on a whiteboard and also project to the screen, a screen of this type.
Yes.
Oh,
Projector, sir.
because for 2 days I dreamed to see how the computer lab looks like, but I didn't see it.
We can visit in the gap because we are having gap now, break now.
Yes, okay.
First we can visit.
It will be very good, yes. So I can switch off this computer. I wish to share with you my experience of working with IFS style. And we can look at this program. This is a program which builds so-called zippers, which I will explain what it is. First I need to say, what is a zipper? This is a special type of self-similar sets, very well known to you because you know von Koch curve and Sierpinski gasket. You know that Sierpinski gasket was built by Sierpinski in the following way. He took interval, yes? Which is the base of equilateral triangle, right? Then he made the following transformation. He replaced, so I draw this interval with an arrow from beginning to the end, yes? And the triangle is above this arrow, so if you go along the arrow, it's on your left side, yes? Then I replace this arrow by, so I take the middle line, yes, and two halves of the sides, and draw the arrows so that triangles above these arrows should lie inside this one. So it will be this arrow, and this arrow, yes? This map, this system is defined by this system of arrows. First map sends this interval to this one, yes? Second map sends this interval to this one, yes? And third map sends this interval, oh sorry, what I made a mistake. Excuse me, this interval to this one. Therefore, the whole triangle will be, that map sends this whole triangle here, right? Because it should be on my left side when I go. This second map will send this triangle here, and third map will send this triangle here. And this picture, not without these triangles, but this trapezoid was shown in the paper of Sierpinski. It was in 1938, I suppose, if I am not mistaken. Oh, no. Maybe 1938 was Levy curve. Sierpinski triangle is something about 1914. I forgot. And then we repeat this transformation to get next iteration of this curve. It will be this one, sorry, and this one, right? Yes? This one, and this one, etc. So zipper is a system of maps which is organized in the following way. We have initial interval. We can consider it is an unit interval, right? And we have some polygonal line with arrows. Yes? And each map sends the whole interval to the beginning and end of each of the subsequent intervals, so that beginning is sent here and the point 1 is sent there. And the direction of the arrow is the signature of this zipper. So the signature of the zipper will be 0, 0, 1, 1, 0. Yes. 0 when we preserve the direction, yes, and 1 if we invert the direction, yes. So here there is a picture when such zipper is constructed. So I will explain it in words. So it begins with the name of the main block. We call it G. Then we write that this block is considered, is checked, because some blocks which are used for some special computations, they are hidden. They are not shown on the screen, but the results of these blocks is used. Then after that, I write the name. So A is attribute, and this is a name. And name will be zipper. So when we begin to look at this, so it will be, after that, we specify the dimension. Dimension is 2. Unfortunately, we can use dimension 2 or 3 only. Yes, in dimension 2 this program works well. In dimension 3 it works also good, but more slowly because the computations are more large. Then there is a special feature of this program. I don't know, because there are many versions of this program, but the author specifies in that way, since angles are measured in radians, he needs to define the number pi, and he defines the pi in this way. Pi is 2 arcsines of 1. So it is strange, looks strange, and we still do not question the author why he does so, because he could just define pi from the very beginning without specifying, and then we begin to define different numbers. For example, when we draw zippers, we used to draw intervals. Yes? An interval can be considered as a self-similar set. So we draw, here it is written in a very good, it's not good manner. So I define interval the following way. Interval, it is not shown, therefore I write ampersand here, is defined as the 0.5 multiplied by union of two maps, first identity, and then, so the vertical line means union. It means union of operators, it means union of objects, so, and star means composition. So this is a definition of the interval. Do I need to explain it? Yes? So you see that x is 1/2 of x union 1, 0 multiplied by x, right? So if we have interval, yes, and interval, we take interval, translate it by 1, 0. This is a translation by 1, 0, yes, and then shrink it to time, for 1/2, yes. So this is a definition of interval, and if I delete this sign, ampersand sign, I can do this. So if I apply this block, then I will see what is defined by it. So here you see three objects which are defined by this zipper. So first it's a polygonal line with arrows, second the attractor, and one more attractor, but we need to change the variables here. So we define interval, and at that moment I delete this sign, ampersand sign, so we can see interval itself. When I delete and apply this operation, then I will see oh, now interval appeared in the list of values, yes, and we can look at it. You see? Okay. 1 second. If you need to magnify it, just do this way. If I wish to magnify it, it is not a problem. I just put the frame here and automatically it will be magnified. The next object which we have here is an arrow. You see these letters? Do you see? Is it visible? I don't know how to magnify the letters. So I deleted this sign and interval became visible. And now I write arrow is equal. So I take interval, unit interval, and make its union with the arrow. So how to draw an arrow? I take interval, I take 0.75, yes, and attach here two small intervals, yes. So here it is written, I don't see, so I take 0.75, 0.75. So what does it mean? AB. In dimension 2, AB means a two-dimensional vector, yes, two-dimensional vector with coordinates A and B, and also each vector defines a translation. So it is not only a number, it's also a translation operator. So if I write AB multiplied by I and T, it means that I will draw the unit interval which is shifted to the point AB. Yes? And if I write AB multiplied by 1/2 multiplied by INT, it means that I have an interval of size 1/2 shifted by this side. If I write, for example, 1, 0, union 1, this is union of two operator. One is identity operator, this is operator one shift. Yes? So I write the interval is 1/2, right, multiplied by union of unit interval and this interval shifted by 1, 0. Okay? Therefore, it is the definition of unit interval as a self-similar set, and this definition automatically constructs the set. What do you wish?
I just want to see the font.
What?
This screen. You come here, sir.
Yes, 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 yes.
Tried it in computer. We view, then setting. Yeah, here we can. So, UI scale. Now you type here something. Thus 10.
What?
This scale you increase. 3.1 to increase.
I think.
Yeah. You go here.
Yes.
It is not.
Oh.
Correct? No, fine. Now you go back. Now you go back. No, no, no. Go back here. Come out from this.
Yes.
Go out.
Yes.
Now is size increase, no?
Oh, thank you. How did you find this? How did you find this? This is wonderful. If also you could show me how to move this screen. Huh? Yes, so I don't need to write anything, yes. Okay, so this is the, oh, sorry. We enlarged the text too much. I need, this program is very sensitive to all kinds of interferences. Okay, that's, so we have, you have, this is, oh yes, I need to explain to you what is ABCD. What does, if we have AB, we have a vector, yes? And vector is also a translation operator. But if we have ABCD in dimension 2, it means, of course, in dimension 4 it would define a four-dimensional vector, but it doesn't work in dimension 4. ABCD is a matrix. Matrix, so ABCD. So this is a fine map. And here you see 1 minus 1/2, 1/2, 1. Sorry, how to erase this thing? Okay. What does it mean? It means that I have unit interval, then I diminish it. I take 7 hundredths, yes, 7 divided by 100, put it here and put two small intervals at the angle which is arctangent of 1/2. Yes. So It's quite good. So this will be arrow. So we define the arrow, yes. And now we define a randomly chosen number from the interval between 0 and 0.5. So it's a comment which is not easy to remember. So I write x1 is dollar number. So if you put a dollar sign, this is some special word in the program or special symbol in the program. For example, dollar name, dollar attribute, and dollar sign number. So we have number, and it is number may be real or may be integer. Yes, so it's real, and since it's real, it can be chosen from some interval. So it is between 0 and 0.5. 0.5 means 1/2. So this is first number. So we have, what does it mean? This means the following. I have 1, 0, I have 1, and I need to define 2 points which are randomly chosen. So this point is x1, y1, and this x2, y2. Yes, and also we have arrows defining this zipper. Yes. So this program defines zipper with 4 vertices and consisting of 3 segments. So here it is. Yes, it is not good that we choose this. I can make it a little better. For example, I can change the number so that this zipper becomes more humane inside in its vision. So suppose I delete this and take this 0.5. Oh, no, 0.25. I take x2 0.75, right? And don't allow y1 and y2 vary too much. So they will be varying in to smaller extent, and I can apply it and look what result we'll have. Wow. Very strange. Very strange. The result is 2. Oh yes, because I look at the interval. A zipper is that. You see? So we have a curve. This is 0, this is 1, this is 1/4, yes, on this line, and this is 1/4. And these are 2 random numbers. So it shows the polygonal line, because when we draw a zipper, we need to see a polygonal line. Yes, and we need to see arrows. So it is very good auxiliary construction, which helps us to make. And let us look at the attractor. You see? So this is the attractor. Is it visible? Okay. Yes, but how to check how this attractor correlates with this initial curve, Z101. This will be this one. You see? So problem may appear how to change parameter. So we have two parameters, y1 and y2, you see? Do you see the parameters? And let us change the parameters, you see? I can change the parameters and the zipper curve changes accordingly. And we can change also the second parameter, so we can put it to the bottom, yes, and this also to the bottom. So when we defined in the program, in the program source, we defined randomly chosen parameters, then we can go to the control window and vary them. So varying them will get different objects and we can attach them. So now there are some special programs, SIM, special commands. They are very simple and I will show how they are defined. If I find the parent block, if I don't find source, sorry, 1 second, not one. Oh, maybe I need to use some editor. Oh, so month. So if we take an interval AB and send it to CD, we can define special procedure which sends this interval to this one. Yes? So it will be SIM of A, B, C, D. Yes? This SIM which sends it sends the interval 0, 1 to the interval 0, 0, xy. So it is defined separately, but now I I need to find it in some programs because I cannot write it. It is very simple. Sim A, B, C, D sends 0, 1 to vector from point AB, CD. So it will be it is the following way: sim of A, B, C, D. B, C, D is it's a translation by AB and composition with matrix. A matrix will be C minus A, B minus D, D minus B, C minus A. Right. Yes. if you so matrix is written in the matrices are written in the linear form, so it will be AB multiplied by C minus A, C minus A, B minus D, D minus B, C minus A. So this sim ABCD means this this abbreviation. Yes. So we have first map sends 0, 1 to 0, 0, x1, y1. S1, 0 sends this interval to the backward interval. Yes. S1, 2 sends 0, 1 to x1, y1, x2, y2. So this map is used for arrows looking to the right, and this map is used for arrows looking to the left. So since we have Z0, Z10, so it has a signature Z101, therefore we use S10 here, then S12 here, and S32 there, because we have signature 1. Okay. So this line shows that we construct a figure from arrows. Yes? So this is Z101, it is here. Yes? And D101 means the attractor, so it's the very zipper, and ZD101 is a composition of these two objects. Okay. Oh, sorry, one. So let us consider some other program. Okay, I don't see. So please look here. This program constructs a fractal square. What does it mean? What it means, a fractal square? A fractal square is a special kind. So, do you know Bedford-McMullen carpets? Yes? Vichek? Okay. If I find it. 1 second. So, let us look at the Levy curve. Oh, no, Levy curve was just... Okay, let us look at the Levy curve. Sorry, but this... do you see it? Yes? So there are many additional components, but the very Levy curve is here. So first, we defined unit interval because we use it for our constructions. Then we define arrow. Then we define something. Oh, this is a, I think this is a square or something like that. Oh no, this is a triangle. You see, this is a triangle. Yes, and S1 and S2 are the two maps. Sorry, what to do with this thing? Yes, these are two maps which define the Levy curve. So if we delete all the other things, so Levy curve is defined by these three relations. I can show it to you how to do this. For example, I can delete all the other things. All the other things. I delete arrows, I delete triangles, I delete everything. And we have a program for constructing a Levy curve. And I will put into some, I will make it Levy curve too and make it one additional block. Yes, so I will proceed to this block. Sorry, I cannot find it. Michik, Sierpinski. No, I don't know. Okay, so look at the Vichik fractal. One second. Vichik fractal. So it is very simple program. So this is the name of a block which means nothing. This is the name of the fractal which means nothing. This is just a dimension, and this is the definition of this set. Do you see? Please look. So we have an operator S, which is 1/3 multiplied by five translations, 0, 0. So if we take a square 3 by 3, yes, then these vertices will have the coordinates 0, 0, 0, 2, 1, 1, 2, 0, and 2, 2. So we take 0, 0, 2, 0, 1, 1, 0, 2, 2, 2. And the operator is Hutchinson operator is contraction, 3 times contraction multiplied by union of these translations. Yes, and K is the image of K under this operator. So the whole program which defines Vichik fractal consists of 2 strings. Yes. So, if you wish to change it, anyway, for example, if I change I can make the following thing: 0 0 2 0 2 0 1 0, 0 0 2 0 1 0 1 2 2 2, and apply it. Then we'll get this nice set. So we just shifted one square to this side and obtained the different attractor. Okay, I don't want to write anything. Or maybe I change. I change it in a new block. And this program is quite complicated because it has dimension 3. Since it has dimension 3, then we need to define, since we have dimension 3, we need to define some other things, because we have translations in different vectors in plane, and then we have rotation. Oh yes, because some parts of this program are defined externally, because rotation x, rotation y, rotation z are defined in the other part of this program, and I cannot look at it from this place. Okay, so maybe we can continue. Which way? I think that I explained most of the things, yes? And it's better to download the program. To download the program, you need to proceed to ifstyle.com. And it can be easily downloaded, yes?
But they are saying some functions are not working.
What?
Some functions are not working. They download.
One which define that similarity.
Yes, because it is defined internally. It's I wrote. So SIM of sorry. How it is SIM.
Okay. You made another program inside.
Yes.
You are calling that function.
Yes, I can show you. Because it is, it cannot be read from IFS style, because it's in hidden blocks.
I understood that you wrote a separate code for that.
Yes, I can show you this one. Yes. I just need to open. I just need to open the other program, but this program cannot be enlarged sufficiently. So this screen is good. Not, I cannot read from the screen. No. I cannot read even to I cannot even look for anything. So the only way is to no. This is absolutely something unnecessary. No, you don't need to.
I just copy.
No, this is not the thing which I am looking for.
You just show me the screen.
Yes,
Show me the
yeah.
screen. What
Yes,
you want to show?
yes.
That
No. I need to open some file. Open. No.
no, why this font is very small?
Because the resolution of the screen is large and this program adapts to this screen. Yes.
Because of
You
that.
see,
Okay, I understood.
the problem of I told you there is a problem of buttons.
I understood.
Which button to press?
Okay.
Other problems are not so huge.
You open, we will copy it in some Word file and magnify it, try to magnify
Yes, but yes, I can do this. So if I switch off this screen,
Okay.
then
Then will be good.
I am freed from this curse. Yes, okay. Yes. So x2 minus x1, y1 minus 1, 2. So I wrote it in more humane form A, B, C, D, and it was better visible. Then y2 minus y1, and then we have x1, x2 minus x1. Yes. So this block being put in your program defines this program SIM, which sends 2 points to 0 and 1 to these 2 points, x1 y1, x2 y2. And also very important function is rotation. It is defined the following way. Rotation is defined, so it is also hidden It is not shown anywhere. Yes? It has a variable a which is initially 0, and it returns a value of cosine of a minus sine of a, sine of a, and cosine of a. So this means that it returns a matrix cosine a minus sine a, sine a, cosine a. Okay. What are else questions? Right?
There is a matrix multiplication there, right?
What?
A 1 by 2 matrix is multiplied by a 2 by 2 matrix, right?
This is a this is an operator of translation, and this operator is a fine map because it's not a matrix. It's a multiplications of operators. Yes. So initially there were very awkward long expression for all this. And the author of this program invented very compact language in which we can we can use sets and operators very freely. So we can apply operators to operators and operators to sets. We cannot apply sets to operators. But in some sense also, because if we have union of operators, so we can apply the union operators to some set or to some operator. So therefore it makes the notation very compact. Yes. Initial versions of this program made by Dmitry Mikhontsev and his friend Alexei Kravchenko, which are dated back to 2000, 3 zeros, yes? Yes, they were very large and awkward. There were many windows, and these windows had to be filled with some symbols. But finally, he came to Kravchenko is a programmer, and he works now in Kaspersky Labs. So he's very busy, yes. But Mikhontsev is also a programmer, but he also works intensely with Christoph Band, yes, because when Band came to know him, so he took him and began to use this program, yes. So I think he works in Huawei, programming in Huawei, but all the time he is making his beloved program IFS style, and it becomes more and more perfect because it is used on its quality and fastness is based on arithmetic computations, which are faster than for example real value computation. Okay. So maybe we need to install this program and begin the practice. I think that I explained main topics, yes, and now I don't need this board. And can we shift to this computer lab? No? What? Ah, yes, they are recording. So I should continue talking. So in this case, I will explain how to build some good zippers. Sorry. Does it work? No? What it is? Source? Can we? No, screen sharing. No.
Click to the source.
Source?
Source.
Yes, I see.
Now it's connecting.
Oh, it is thinking and okay. Oh no. Okay, so let us begin with von Koch curve. What kind of fractal do you we supposed to build now? We can make, for example, we can construct some kind of a deformation of von Koch curve. So suppose we have an interval. We divided it into 4 parts. Yes? And then we begin to move this point to that position. Yes? We will try to deform this. So we consider this zipper. It will contain the point 0. This will be, for example, 1/3. This will be 1/2. This will be 2/3, and this one. Yes. We need to define the self-similar set, and we're supposed to change this parameter from 1/2 to 1/2 plus h. Maybe let h belongs to interval, for example, from 0 to how large can we choose? I think it's better to 0 to, or maybe 0.4. Not so much, yes? And we're supposed to make this. So we defined 4 maps. First map will send this interval to 0, 1/3. S1 will be 1/3. S1 will be just 1/3. S2 will be, really it will be a map which sends 0, 1 to 1/3, 1/3 0, and 1/2 h. Yes? So it will be sim of 0, no, 1/3 0, 1/2 h, right? S3, if this will be a zipper with signature 1111, S3 will be SIM, it will be 1/2 h and then 2/3 0, yes, and S4 will be 1. So we need to make 1/3 contraction of the interval and then translation it by 2/3. So it will be 2/3 0 multiplied by 1/3. So we defined these 4 operators. If we don't try to define this SIM, then we can write it directly. So write directly, it means we need translation to 1/3 0. Yes, and then we need to make such a rotation. So it will be a matrix which sends 0, 1 to this one. So we find this difference. This difference is 1/6, yes? And this difference is h, right? Is h. Therefore, the matrix will be 1/6 minus h, h 1/6. Right? The matrix which takes the interval 0, 1 to the interval with coordinates 1, 6 and h is the following. Right? Okay. And here we have also the same things. We have we replace this, I will write this here. S3 will be translation by 1 second h and a rotation by this to 1/6 h minus h 1/6. Okay, so we'll write these things. So we draw write h is a number, it's real, it is taken from interval from 0 to 0.4, yes, and And then we have to write that K is equal to S1, S2, S3, S4 multiplied by K. And this will give us this curve which deforms from interval to von Koch curve. I can make it the following way. I have this program and I can write here along with Wittig fractal one more object which is specified this way. So I begin editing the program, you see. First I need to define this, this vector H. So I write H equals number which is real, and it is changing from 0 to 1/4, right? 0.4. 0.4. Then I write, so being very lazy, I just write the equation. I called it KK, Koch curve, and I write this four maps. First, I take the union of 1 and translation to 2/3 0. I take the union, and the union is denoted by a vertical line. I don't know why, but it is very convenient. You see? And then I multiply it. Oh, sorry. And multiply it by 1/3. Then I multiply this by 1/3. And then I take the union of this operator with two very long operators. Very long operators. How to do this, I don't know. Maybe I will act the following way. It is more convenient. So I type it, so 1/3, 0, right? Then press star, 1/6, then it will be minus h 1/6, 1 6, right? And second will be second will be second will be 1/2 h, 1/2 h multiplied by the similar thing, it will be 1 6 h minus h 1 6 right? And all this, we unite all these operators in one union. Shift 1. Then and apply it to kk. Okay? And now we need to apply. If everything is without mistakes, then it will work. So it applies. Okay. Then you see, there is the result, and this result can be changed because we can change the parameter. So, you see, it works. Are you satisfied? Of course, we are not satisfied with the number which we with the restriction on the numbers. Then we can make minus. Yes. And even make minus 49. Yes. So, are there any questions?
So show us the source code again. That
What you say?
so show us the code that you have written once again.
I don't hear.
So please show us this again so that we can get what you have written here.
Ah, yes. 1 second. 1 second. I need to go there. And the source is here. What?
We are not seeing the whole code in the last line.
We don't see the whole code. No, this is the whole code. You mean you need to see other blocks? Oh,
Discrete.
no.
Code towards the right.
This block is shown completely.
So there is one more block to this, na?
No. Ah, you mean that the line is longer.
Yes.
Sorry. I can improve the situation, yes. This is no problem. It will read. It won't suffer if we write the operators in this way. This program doesn't suffer from this. Let us check. Yes. Okay, and oh no, sorry. Oh. Source, and we can change the parameters, controls, yes? So nothing changed. Yes, but of course we can change some other parameters, something like this points 1/3, 2/3, and all this. Yes. What?
Switch to the source.
Yes, 1 second. So now this block, wow, sorry. So now this block doesn't correspond to its name because there is not only Wittek fractal, but also we have this transformation on von Koch curve. Okay. Okay. Oh, so let us make some other things. Maybe we can make some deformation of So in this program you have the Wittek fractal, you see it, right? It is here, right? So consider the following problem. Yes, we have a Wittek fractal. It is obtained by sending the square to these 5 smaller squares. Can I continue? Yes? Thank you. Let us do the following transformation. I suppose to rotate each of these squares by some angle alpha. Yes? I mean, I take a square, yes? Then I have some rotated square here, a rotated square here, a rotated square here, and rotated square here. They must be of equal size, yes? Right? And then connect them by this square. So it will be a deformation of this Vicek fractal. And suppose to look, let us look how this deformation will look like. But this is not very easy, but it is possible to do. Fortunately, these angles are the same. And these four maps are also the same. Since these four maps are the same, we can construct them in two scratches instead of 8 ones. So we have here some vector, yes? Maybe let us define this vector by AB. Yes. So A will be approximately 1/3 or something like that, and B will be some negative value, maybe minus some kind minus H. So it will be A minus B. So and B belongs to some interval between 0 and say 1/6. Yes? Okay. And then let us consider the map which sends the whole square to this distorted square. It is not a problem. This map sends, if this is the unit interval, this map sends unit interval to A minus B. So this map can be written in the form A, B minus B, A. Right? This map is defined by the matrix A minus B minus B, A. Can you check this? Let us consider. If you have this matrix A, B minus B, A, and apply it to the vector 1, 0, what you have? B, no, A minus B. So this vector goes here, right? A minus B. And if I take the vector 0, 1, I will have this BA, right? So this matrix was defined correctly, okay. Now we need to find, then we have this matrix, and it will be repeated 4 times, but it is not good to use it, right? Oh, how to use this? Since they are look the same, but they are different, right? In which sense they are different? If we consider translations, then we need to consider these 4 points. It's easy to find them, but not very easy. Yes, but if we use the symmetry, it will be much more simple, because do you know what transformation sends the square to itself and rotates it by 90 degrees? can you write the transformation which sends the square, unit square, to itself, but rotates its vertices? Do you understand? So it sends 0, 0 to 1, 0, 1, 0 sends to 1, 1, and 1, 1 sends to 0, 1. So it's a rotation of the square with respect to 0 plus translation by 1, 1. So this map will be 1, 0 multiplied by 1, 0. No, sorry. 1, 0. We need to make this rotation which sends 1, 0 to 0, 1 and 0, 1 to minus 1, 0, right? So it will be 0, 0 minus 1, 1, 0 or not? 0 minus 1, 1, 0. It sends 0, 1. 1, 0 where? It goes 1, 0 goes to which vector? 0, 1. Okay, it's true. Yes. And if we applied it to 0, 1, it goes to minus 1, 0. So it's just the rotation which we needed. So you see, it's easy to consider theoretically, but when you begin to make constructions, you need to check possible appearing mistakes. Therefore, it's better to test mistakes in advance. Okay, so this operator will be, as I said, 1, 0 multiplied by 0, 0 minus 1, 1, 0. Yes? And it will be A, for example. It will be A. So I define this operator A. Yes. So we defined this rotation, then apply operator A, we apply these 4 squares, right? Using symmetry, but we need to define this one. What it is? What is this vector? Do you know it? So it's A minus B. This is B minus A minus B. This is BA, yes? So it will be A plus B A minus B, right? This vector is A plus B, A minus B. Do you agree? Okay, it's okay. A minus B. And what's about this one? So we need to apply this rotation to this vector. So we need to, it will be, this distance is second coordinate is a plus b, right? And first coordinate is 1 minus a minus b. 1 plus b minus a. Please check. I'm standing near the blackboard, so I have a very large risk of making mistakes. Right. So did you check? No, okay. I don't play such games. Please, please check. So this coordinate will be a plus b, a minus b, and this coordinate will 1 plus b minus a plus b. So we need to define this vector, yes, and it is 1 plus b minus a minus a plus b. Wow. Oh, so it's 1 minus 2a, right? B is y minus 2a, y minus 2a, right? And second coordinate will be a plus b minus a minus b to a plus b to b, y minus 2a to b. Okay. Now we are in charge to write this deformed Vichek set. So it will be the following things. So we defined, you see, we defined the rotation, which makes this square, right? What is the rotation? It is a minus b, ba, right? This map sends the unit square to this one. Yes. And this map, it will be a plus b, a minus b. This point multiplied by rotation. Oh yes, multiplied by rotation. 1 minus 2a minus 2b, y minus 2a. So this map sends this square to this one. Okay. We can write the command. Oh, yes, also, can you remind me what was the A which I erased just now?
Closed interval 1, 0.
What?
Closed interval 1, 0.
No. This was a rotation. It was first. Yes. 1, 0 multiplied by minus 1, 1, 0. 1, 0, yes. It was A. Right. So we have to write the following way. So the operator will be 1 A multiplied by A multiplied by A multiplied by A. It's not very optimal, but it's good. We have 3 rotations. Then we multiply them by this map A minus BBA, BBA, right? And then add here this one. And add here this one. A plus B, A minus B, and this composition 1 minus 2A, 2A minus 2B, 2B, 1 minus 2A. If I didn't make a mistake, this will give us, this operator will give us this deformed Wiechert set. It will give us this deformed Wiechert set, and we need to type it down in our laptop and check if it works. So maybe this way, not sufficient number of degrees of freedom. Because I need to see the blackboard to make the computations. Okay. So first I define A. A is equal to 1, 0 multiplied by 0 minus 1, 1, 0 multiplied by 0 minus 1, 1, 0, right? And then we have this map. We have T. It is equal to 1 composition A. Composition A multiplied by A. Oh, sorry. Does anyone repeat these things? No? Does anyone try to do the same? You are doing, yes? Oh, that's good. So, and it will be A star A star A. We close it and then apply it to A minus BBA. Apply it to A minus BBA. A minus B. Sorry. B A, right? Not wrong, because I have a bracket. Yes. And then there is a vertical line, yes? A minus BBA, right?
A plus B, A minus
Yes, but there is a vertical line. We need to make a union of two operators. We make a union of two operators, and this one will be a plus b, a minus b. It's a translation. A plus b, right? Sorry. A minus b, right? Oh. And this is multiplied by 1 minus 2a minus 2b to be 1 minus 2a. Minus 2 star b, 2 star b, and 1 minus 2a. 1 minus 2 star a. Okay. So this is the operator T. I need to define A and B. Let us A and B be, say, 1/3. Oh no, yes. We need to define them some way. A equals 1/3. B equals 1/6. Right? Yes. And after that we write k. Oh no. K equals T multiply k. So if everything is correct, it will work. If not correct, it will give undefined variable. Sorry. Okay. Oh, no problems. Let us check if we have this. If we have. Do you see? It works. And now we can change some. So the problem was solved without mistakes. It's a great victory. It's a great victory because just without preliminary computations, just from scratch, it was done without mistakes. It's maybe it's first time in my life. First time. Yes. Now we need to make changes. Make changes because A. So we have H. Instead of H, we can use A. Oh no. Okay. Instead of let B be equal to H. Well, let B be equal to H divided by 2. Not so large, because, and then we can change H and we can deform this thing. This pure thing will be deformed and we can see the deformation. 1 second. Apply. Okay. Wow. Yes. Very strange, but it doesn't work. By some strange coincidence it worked, and at that moment it stopped. It stopped. So let us change the parameters. So h was yes. It was a there is some small mistake. Some mistake. Yes. There's some mistake in our computations, but it is not for today. There was some very strange success. What is this? So we need to make some error checking, and after this error checking it will be improved. Most probably these computations were not correct. Somewhere the sign was changed. Let me check again. Oh, different sign. Yes, it should rotate a different direction.
Instead of minus b, b.
Yes, yes, instead of minus b, it must be plus b minus b.
And for minus 2b, it should be 2b and minus 2b.
Right, but let us check. Ah, yes, 2b and minus 2b. To be or not to be, yes, okay.
And sir, a minus, instead of a minus b, ba, it should be a b minus ba.
Oh. Let us make improvements step by step, because it is wow, very interesting. So I change to b to minus to b, right? And something, yes, controls. Yes, there is a. I need to use some kind of sheet of paper.
You can change a, then b, then minus b, then a. Just below the function t where every class.
Let us check. Yes, I will follow your wise advice. Yes. Maybe it will do. It will. So I need. Sorry. Editor. A. No, no, no. A minus BBA. A minus BBA was, oh yes, apply. It is rotation this in, oh yes, A minus BBA rotates counterclockwise and I need to rotate it clockwise. B, A B minus BA. Because B is positive, right? But in that case, we need to change this. Translation. Play, yes. It looks great, but most probably we need to change all these signs. Okay, play. Now.
Should be A plus B, A minus B. Yeah, A plus B and A minus B.
Oh, do you apply the some random changes? No? Oh. Sorry. Oh. Controls. Ah, you're a genius. You're a genius, yes. Thank you, thank you. You saved all this example, yes. Fantastic. Fantastic. So we can change H to yes. Right. So the problem was solved. Yes. By very intense and effective cooperation. So what is the time now? Huh? And when we finish? What?
We have to finish by 5:45.
And now it's... So we need to continue till next 5:45. Okay. Yes, okay. Okay, so we continue. Huh? We started late. So we need to continue till 7. No.
Continue tomorrow. Now we can start.